All right, so this is our first lecture on covalent compounds, and this lecture is on Lewis dot structures. And just kind of a general introduction to covalent compounds in general. So covalent compounds are compounds which are bound together in a different way than our ionic compounds. So this is versus ionic. Ionic are different. So everything we just learned in our last chapter, we're just going to kind of ignore it for a minute as we talk about our covalent compounds. So the ionic compounds are nearly always made of metals with nonmetals, because metals want to give away their electrons and nonmetals would like to gain electrons. And so it's kind of a nice convenient match. But a covalent compound happens when you have two nonmetals bound together. Because here now, whoops. Both the nonmetals want to gain electrons. So they're not going to make an ionic bond with other nonmetals because the other nonmetal is not going to give away their electrons. So instead, they have to find a different way to make it work. And what they do is they share their electrons. And we are going to show this sharing or kind of visualize that using these Lewis dot structures. So let's start with some very simple Lewis structures. Essentially what we do is we look at the periodic table and we see how many valence electrons does an atom have, and then we put dots around the atom to indicate the number of valence electrons. So I'll let you guys help me remember how do I look at the periodic table and know how many valence electrons something has? Paste the periodic table here. Right, if I'm looking at this, Erica is totally right. I'm just going to, this only works for main groups, but I'm just going to number it and say everything in group 1 has 1 valence electron, and everything in group 2 has 2 valence electrons, and everything in group 3 has 3 valence electrons. This is because of 13. Sometimes they call it 3b or 3a, it doesn't matter. And then we've got 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and then everything here has 8 with, of course, the obvious exception of helium because he only has 2, right? Now this isn't the total number of electrons. This is the number of electrons in the outermost shell, which are responsible for the chemical properties. So these, as we call that, are valence electrons, valence being the outermost shell. That makes sense, right? You guys can figure that out? You do get the periodic table on, I'm going to open my workspace here. Do you get the periodic table on your exam? So that's something that you're going to want to be really familiar with. Will I test you on any transition metals? Not on knowing valence electrons. I will not. I will test you if I give you a compound, an ionic compound that has a transition or post-transitional metal. You should be able to deduce the charge, but they won't apply for covalent compounds because, again, covalent compounds is 2 nonmetals. So we're making covalent compounds mostly with these elements only, okay? And even though the noble gases are nonmetals, they still don't react, but hydrogen also will react. Here we go, to make covalent compounds. So these are the elements that we're using to make covalent compounds. And if you are a pre-health science major, which many of you are, then you'll want to note that organic compounds in the body or in nature are primarily covalent compounds. And so you'll see these elements and these type of compounds primarily, if that makes sense. Okay, so we're going to take these little guys and we're going to represent them as Lewis dot structures using little dots. So we're going to say, oh, the hydrogen atom can be represented as having, we're going to put the symbol there, And then we're going to put a little dot here to represent his 1 valence electron. Or we could say carbon here has 4 valence electrons, so we're going to give him 4 dots. And we're going to put dots on each side, top, bottom, left, and right, before we start pairing them up, because it turns out that electrons like their space. They don't want to pair up unless they have to. Now for nitrogen, they have to start pairing up. So 1, 2, 3, 4. And then it literally does not matter where I put the 5th electron. I could put 2 on the left, or I could put the 2 on the right, or I could put the 2 on the bottom, or I could put the 2 on the top. It does not matter at all. Just so long as nitrogen has 5 electrons and 2 of them are paired, then you've got the right Lewis dot structure for that atom. Then oxygen, of course, comes in and he has 6 valence electrons, so he's going to need 6 dots. So we're going to give him 1, 2, 3, 4, and we need 2 more dots. Again, it doesn't matter which sides end up with pairs and which sides are unpaired. I could happily do this, and that would work just fine. And then fluorine here has 7 valence electrons, so we're going to put 4 on the outsides. So this is how we represent it for individual atoms. Now, this is just the beginning, right? Because we don't want to know how to do it for atoms. We want to know how to do this for compounds, but this is just to show you how we get started. Does this make sense to everybody? Any questions on that? Okay. So then when these atoms come together, right, let's say hydrogen is going to bond to fluorine, like as for instance. There we go. Take one of each of these. And hydrogen has 1 electron, and he'd like 1 more, because if he has 2 electrons, then he'll have the same electronic stability as a full shell like helium has. And fluorine has 7 electrons, and he wants 1 more, because if he gets 10 electrons, he'll have the same number of electrons, feel like neon, have that same stability. So they both want 1 more, so they're not going to both give away or have one person give away and one accept. Instead, they say, look, what if I move, let's see, no. What if I flip you here? There we go. What if we come together like this? And we spend some time together sharing these 2 electrons. And hydrogen's going to donate this electron, and fluorine's going to donate this electron. And then together, the hydrogen can feel like he owns 2 electrons because he's sharing one of the ones from fluorine, and it's in his space. And then fluorine can feel like he owns 8 electrons because he's sharing one from the hydrogen. It's in his space. And that shared set of electrons we call the covalent bond. And we can represent it exactly like this with dots, or actually it's a little bit easier to visualize, I think, if you use a line there. That's your covalent bond. This is different from your ionic bond, which was just an attractive force. Here you actually have electrons there being shared between the 2 of them, and that sharing of electrons is the basis of that relationship. Okay, we said our ionic compounds were like high school relationships because there was just this intense attractive force. I'm going to say the covalent bond is like a marriage because there are assets involved. They cannot just separate because who gets the assets? They're going to have a fight. Both of them want the electrons, right? And so that's a much harder bond to break, the covalent bond, than it is to break the ionic bond, if that makes sense. Are you guys with me here? Okay, so we're going to share electrons this way. Now we can do this kind of eyeballing, just like I did with the fluorine and the hydrogen, right? And you can go on and say, okay, if I made a compound with nitrogen and with hydrogen, you can see nitrogen wants to make 3, it has enough electrons to make 3 bonds. And hydrogen only has enough electron to make 1 bond. So if I made a covalent compound between nitrogen and hydrogen, then how many hydrogens do you think would attach to the nitrogen there? Erica says 3. That's exactly right. There's enough space for 3 hydrogen atoms there. So we could put 1 here. Perfect. And we could take another one. Whoops, that's not what I wanted. Go. And we could take another one and put it there. Plus hydrogen for being such a symmetrical element, eh? Okay. And then we can take another one and put it there with his dot here. And if we do that, I hope you guys can see it works really nicely for nitrogen to make 3 single bonds to hydrogen atoms. They can fit 3 hydrogens on there, and now each hydrogen feels like he has 2 electrons. And then the nitrogen feels like he has, how many electrons does he have? 8. Perfect, Erica. See? He's got 8 there, which is perfect. That's what he wants, right? That's the idea. When we made an ionic compound with nitrogen, we said he wants to gain 1, 2, 3 electrons to be like neon. So instead of having 5 valence, he wants 8 valence. But that's what we're going to see with all of these as we make our covalent compounds. Everybody wants to get to 8. Everybody wants to get to this column right here. So that means everybody wants to get to 8 except for hydrogen, which only has 1. He's aiming for 2. Does that make sense? Hydrogen's happy with 2. Don't give him any more than that. But 2 for hydrogen, 8 for everybody else, and that's our goal, to make everybody happy. You guys with me? Yes, everyone will be 8. Alexander, everyone will be 8 at the end, except for hydrogen, which will be 2. That's what he needs for a full shell. There are some other exceptions I will not test you on. I'll tell you about them though, because you'll see them in Mastering Chemistry. All right, let's try this right here. I don't know if I can get a bigger one here. Oh yeah. Okay, so this is, again, directly from your worksheet. We're going to draw the Lewis dot structures for these compounds, and we're going to do it this time by doing what I did above, which is I'm going to write the individual ones. So I've got chlorine and I've got chlorine, and each chlorine has 7. So I'm going to write these in 1, 2, 3, 4, 5, 6, 7, and I've got 1, 2, 3, 4, 5, 6, 7, and then I'm going to put it together. So I note that each chlorine has 1 unpaired electron that can make a bond. So I'm actually going to, hang on, I'm going to move this guy over. I'm going to move those electrons down here. There we go. Now I've got 2 chlorines, each with 1 unpaired electron, and I can put them right there together, and they'll be super happy. And you can leave the dots if you like, but I like, there's so many dots that it's easy to get kind of lost in the dots. So I really like to have the line there instead. Does that make sense? Okay, let's do H2O. Br2 is going to look the same as Cl2, actually. I want you to note, because both chlorine and bromine have 7 valence electrons in their outer shell, that electronically they're basically identical. They're going to do the same thing. All right, but for H2O, I've got an H and an H and an O. And O has 6 valence electrons. Just look at the periodic table to know that. 1, 2, 3, 4. And now I'm going to be wise about where I put my last 2 electrons. I'm going to put them top and bottom just to make my life easier, but it does not matter. Does not matter one bit. So then I can bring 1 in here. Flip that guy. And I can bring 1 in there. Does that make sense? And if I want, I can turn that into a line. It's also good. Okay, now this works well. This method works well for very simple Lewis structures like Cl2 and H2O. But we've got some more complicated options available to us as well. And when we are drawing Lewis dot structure for things that have a little bit of a more complicated structure, then we have to, we're going to have to follow some more advanced rules, okay? And I've got these rules in your lecture notes. I'm going to copy and paste them here, and you're going to want to memorize these rules, because the deal is, if you memorize these rules and you follow them, then you will always be correct. And I think that's valuable to you guys, right? You guys want to always be correct on your Lewis dot structures, even when they're tricky and complicated? Yes, yes you do. Okay, so let's look at these rules. Now, in these previous examples that I showed you here, we allowed chlorine to come in with 7, we allowed chlorine to come in with 7, and we let them kind of naturally come together and make a bond. In these examples, we're not going to let the atoms keep any of their electrons. I'm not going to start with nitrogen having 5 and each hydrogen having 1. Instead, I'm going to take all of those electrons and then I am going to distribute them as I see fit, such that everybody gets a full shell, because that's what they want to be stable. And in the process, you might find that you have more or fewer electrons on an atom than you normally do, but there's no other way to predict it without going through this process. So that's why these are tricky and they take a little bit of extra work. Okay, so here's our rules. Number 1, count the total number of valence electrons available. This is the sum of the valence electrons in each of the atoms bonding. If the structure is that of an ion, then remove or add a number of electrons equal to the ion charge. So the number of valence electrons available for bonding on NH4, we would say nitrogen is in group 5, so as an element, it comes in with 5 valence electrons. So yes, those are available for bonding, but I'm not going to give them to the nitrogen yet. Then we have 4 hydrogen atoms, and they each come in with 1 valence electron. And finally, there is a charge, and a positive charge means I am missing a negative charge, and electrons have a negative charge. So overall, I've got the 5 from the nitrogen, the 4 from the hydrogens, and I'm missing 1 electron in the overall structure because 1 has been lost. So overall, 5 plus 4 times 1 should give me 9, minus 1 gives me a total of 8 valence electrons. Did you follow what I did there? Does that make sense? Okay. Erica's with me, Nicole's with me. It's totally fine. We're going to do this several times. So we'll get extra practice. But this one right here, that positive charge, meant that I lost an electron. Just the same as it was when we were looking at ionic compounds, right? That if you have a positive charge, then you must have lost an electron. Okay, so that was step 1. Now it says step 2, I'm going to arrange the atoms in order of connectivity. And then step 3, I'm going to connect them. So in fact, I can do these kind of together. Steps 2 and 3, we're going to say, look, unless otherwise noted, or if it's hydrogen, the first atom listed is the central atom. So we're going to put nitrogen in the middle. That's what they say. Nitrogen goes in the middle. And then everything else is connected to it. So we're going to have 4 hydrogens. And again, we got top, bottom, left, right. 4 hydrogens, there we go. And then step 3 was to connect them with a single bond. Now, the idea here is that if I don't have at least a single bond between the central atom and the exterior atoms, then I'm not part of the compound. If I'm not bound to the molecule, I'm not part of the compound. So I have to have a single bond. So that's why we start with a single bond. And now, before I continue, I'm going to check to see if I used up all of my electrons, because the rest of this says, how do I distribute the remaining electrons? I want to know how many I've got left. So you guys tell me, how many electrons have I used to make single bonds between the nitrogen and each hydrogen? I've used 8. There are 4 single bonds. Good job. 4 single bonds, and each single bond consists of 2 dots, right? Two electrons, which are shared. And so I have actually used up 8. I don't have any more electrons. I'm out of electrons. Ooh, okay. Well, that means I'm going to skip step 4 because I don't have any remaining electrons to distribute, and just go straight to step 5, which says I need to evaluate my structure. Make sure that all the rules are being followed. Mostly I'm looking for, does everybody have a full shell? So remember, for a full shell, each hydrogen wants 2 electrons, and every other element is going to want 8. Do I have that? I do. Yeah. Each of my hydrogens has a single bond, that's 2 electrons. And then the nitrogen, because it has 4 single bonds, that's 4 times 2, that's 8 electrons. I am done. I did it right. Now, it is a common practice, if you have an ion, to put that in brackets and give it a little charge up here to remind people that it's an ion. I could deduce that by counting and say, I only have 8 electrons. Hey, if I put nitrogen and 4 hydrogens together, I would expect 9 electrons. It says there's only 8, there must be a positive charge, but that is a lot of work. And so if you are communicating the structure to somebody else, to make sure they don't have to do that work, it's appropriate to put it in brackets and put a little charge up there to remind people that it's there. Now, this is an unusual structure. I mean, it's easy. It seems like it was simple to do because we followed the rules. But it is unusual in that we would have predicted typically that nitrogen makes 3 bonds because it has 3 unpaired electrons, as you can see, just like it did in this structure. And yes, it does like to make 3 bonds. So this is an unusual structure. We couldn't have used this method to put it together because we wouldn't have known kind of what to do with this extra spot where I can't make an extra bond there. Does that make sense? But if I followed the rules, it just was slick as a whistle, came right together. Should we do another one? I say slick as a whistle. You guys might be like, yeah, that was not simple to me. You might find that to be not as straightforward. Okay, but that's why we're using these rules, because otherwise if we tried to puzzle piece it together like that, it doesn't work, right? That puzzle piecing together, as we did up here, works for many compounds, many simple compounds, but it's not going to get us there every time. You might ask, why did I even teach you this if I'm going to teach you a better way? Mostly because I want you to have an idea of how they could come together, but also because I often find students who were taught this, like in high school, and so they think that it's okay to keep doing that even when I teach them these rules, and I want to show them that it will not help them. Okay, let's do SO2. So step 1, now that I've shown you guys how to do it, you can help me here. Count the total number of valence electrons available. How many valence electrons do I have here? 18. Good job. 18. So sulfur's in group 6, so he comes in with 6. And oxygen is also in group 6, and there are 2 of them. So I have 6 from the sulfur plus 2 oxygens that each have 6. That's like saying 3 times 6. I have a total of 18 valence electrons available to distribute in this molecule to give everybody a full shell. Good. All right, step 2, arrange the atoms in order of connectivity. Which is the central atom? Unless otherwise noted, or if it is hydrogen, the first atom listed is a central atom. So it's got to be sulfur is in the middle, and we're going to have oxygen on either side of it, like this. Right? Okay, this is step 2 and 3. So we're going to give them some single bonds here. So we put them around this way, and then we're going to connect them with single bonds, because if they don't have at least a single bond, then it's not part of my compound. Okay, just to review, okay, now I got that. It's, again, it is 18 because you're looking at the periodic table and saying oxygen and sulfur here are both in group 6, so they each come in with 6 valence electrons. Okay, oops, too far. All right, everybody feel confident about steps 2 and 3 here? Okay, so next we are going to distribute the remaining electrons. And before I distribute them, I need to know how many I have remaining. So how many have I used up here? I've used up 4. I've got 2 single bonds, and they each consist of 2 electrons. So I'm using 4 electrons out of the 18. So how many do I have left? This is probably as good a time as any to inform you all that on this exam, you're not allowed to use your calculators. Now, there's no dimensional analysis on this test. There's no formulas on this test, but you do have to do this kind of math on the test without your calculators, which shouldn't be scary, but many of you have become accustomed to checking your work on your calculator. And so I recommend just kind of polishing up those addition, subtraction, multiplication math facts that will help you on this upcoming exam. Okay, I've got 14 electrons left, and I'm going to distribute them in blue just so I can tell the difference between the ones that came in steps 2 to 3 and the ones that are in step 4. All right, so step 4 tells me to distribute the remaining electrons like so. First, I'm going to add electrons to each exterior atom until they have a full shell. So the exterior atoms get the first, and then if there are any remaining electrons, then they go to the interior atom. So outside atoms first, inside last. Okay, so I've got 14 left. Each oxygen has 2 electrons because of that single bond. How many electrons do I need to add around each oxygen so that it has a full shell? 6, that's right. They each have 2. They want 8 for a full shell because everybody wants 8 for a full shell except for hydrogen. So I'm going to add 6 more. So 1, 2, you know what? 3, 4, 5, 6. Oh, that's so much nicer. 1, 2, 3, 4, 5, 6. Great. Okay, how many electrons have I used to put a full shell around each exterior atom? Oh, sorry, just for this portion, just for step 4A, how many did I use? I used 12, right? 6 times 2, I used 12. So how many do I have left? I've got 2 left. So now I can move to step 4B and put the remaining electrons on the interior atom. So I'm going to put those last 2 electrons right there on the sulfur. And now I can come back here and say I've used my last 2 electrons, and now I'm all out of electrons. So now I can move to step 5. So just to kind of clarify, this is what we started with. This is what we used to make single bonds, connect atoms. This is what we used to fill shells on outer atoms. And this is what remained to go on the central atom. And now we're out of electrons. Okay, oh, we're not done. We're not done, Nicole, because we got all the way here, and now we've done step 4b, so now we have to evaluate the structure. And we say, does everybody have 8 electrons? Yes, Sylvia, the bond consists of 2 electrons, yes. That line is 2 electrons. So what you see here is oxygen has 8, right? Because he's got 2 from the bond and then 6 dots. And the oxygen on the right has 8 because he's got 6 dots and 2 from the bond. And the sulfur in the middle has 2 from each of the bonds, that's 4, and then 2 from the top. So the sulfur in the middle only has 6. So this is where we say, oh man, I don't. If they do not have a full shell, I need to share more electrons by forming a double and or triple bonds. And I'm going to do that by bringing electrons from exterior atoms. Okay, so what I'm going to do is take 2 of these electrons on one of the oxygen atoms. It doesn't matter which oxygen atom, but I can't take, say, 1 from each. I need 2 from 1. So I'm going to take these 2 electrons from that oxygen atom, and I'm going to move them to the space in between the 2 atoms. I'm going to move them right there. So oxygen basically is taking those electrons and pushing them in and saying, look, I'll share with you. Well, they were right here, right? So it's pushing them in and saying, I'm going to share these 2 electrons with you instead of owning them myself. And so now the oxygen on the left has 8 electrons still because he's got 3 lone pairs of electrons or unbonded electrons and 1 bond. The oxygen on the right still sees 8. Because even though he's sharing more, he still gets to pretend like he owns those, right? He still gets to say, I've got all 8 of those. Now, 2 that are unbonded and 2 sets that are unbonded for 4 electrons and 2 sets that are bonded for 4 electrons. So he's still got 8. And now the sulfur in the middle, having 3 bonds and 1 unbonded pair, has 8. Can you guys see that? Again, it doesn't matter which oxygen I use, but I have to pick one. They're identical. Now, I also want you to remember that each of these came in with 6. So if I tried to give each of those 6 and puzzle piece them together, I couldn't get to the structure because right now, this oxygen appears to have 7, right? He has the 6 that he owns here, then we'll say he owns this one of the 2. This sulfur appears to have 5, right? Like he owns these 2 up top and then he can only lay claim to 3 of these ones that are being shared. And this oxygen does have 6. So it's kind of, you wouldn't ever come up with this structure by trying to just puzzle piece it together. But then again, you couldn't get it to work puzzle piecing it together. You couldn't come up with any structure by doing that. Does that make sense? You with me? Okay, let's do our CO here. That looks simple enough, right? Shouldn't be a problem, hypothetically. All right, step 1, how many valence electrons does my CO have? 10, perfect. I've got 4 from that carbon, and I have 6 from that oxygen because carbon's in group 4 and carbon's in group 6. So I have a total of 10 valence electrons available. So then steps 2 and 3, there's only, you could say carbon central, but there's only 2 atoms. So we're just going to put 2 atoms there. That looks pretty simple, right? Pretty straightforward. All right. And I've used up, I'm going to move this down here. How many electrons have I used up to give it a single bond there? Good, I've just used up 2 electrons. Okay, so I can subtract 2 from my 10. How many do I have left? I've got 8, okay. Then the next step says distribute the remaining electrons on exterior atom first, so they have a total of 8. Follow the rules. Do not say, well, there's 2, so I'm just going to put like 4 on each or whatever. No, 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 ma'am. No, sir. We're going to pick. Carbon gets to be central, so we're going to put on exterior atoms first. Here we go. Oxygen's going to want 6 more because he's got 2 from this bond, right? And then we will have 2 left. And we're going to put those remaining 2 electrons on the interior atom. They're going to go right here on my carbon. Well, now I've used up those last 2 electrons, and I'm all out of electrons. And so now I move on to step 5 and evaluate the structure. I see that the oxygen does have 8, and it should because that was the point of step 4A. And that the carbon does not have 8. And I'll tell you, if anything does not have a full shell, it's going to be the interior atom because it's always the last one to get electrons. So this carbon has how many electrons? He's only got 4. Hang on, I'm going to draw this out a little bit better so you can see. So he only has 4, right? He's got the 2 that he owns and then the 2 that are being shared. So oxygen is going to want to move 2 of those electrons in so that carbon can have more electrons. So I'm going to move these 2 electrons into that space between the 2 of them. Right there. Now does carbon have 8 electrons? Yeah, Erica sees it. She says carbon does not have 8, he only has 6. So we're going to move another set of electrons in there. And we're going to make a triple bond as those electrons move to the inside. And now does he see 8 electrons? Yes, now carbon sees 8 electrons. Oxygen sees 8 electrons. And therefore we can assume that this is the correct structure for that compound. And now it's kind of colored, so it might be easier if I redraw this. Carbon has what we call a triple bond to the oxygen, and both the carbon and the oxygen have 2 electrons. This is, if you look strictly at how many electrons they strictly own, if you're not sharing, right? They each see 8, but if you looked at what they own, you'd say, well, the carbon has 5 and the oxygen has 5. And that would be kind of weird because carbon came in with 4 and oxygen came in with 6. But the stability that comes with having a full shell is more important than the stability that might come from having the number of electrons you came in with, right? So that's why we go with this model. How do you guys feel about these? Good. If you're feeling like, theoretically, possibly, but practically it seems a little scared, do know that practice makes perfect on these. And that because I know that, I've given you lots and lots of practice. If you look at your covalent structures worksheet right here, then we start with just doing individual dot structures, and then these are the simple ones where you can puzzle piece them together. And then you have here are 12 more for you to practice following the rules and going step by step. If you get stuck somewhere, know that it's the challenge is that you didn't follow the rules somewhere. Maybe you miscounted the number of electrons. Maybe you put the wrong thing as the central atom. They can be challenging. Okay, let's take a little break. We'll come back in about 5 minutes and we'll talk about shapes of covalent compounds.